Hello, from TransWave Photonics. Today I'd like to brief you on the status of our mid-wave IR LED array for infrared scene projection, an SBIR Phase 2 research project sponsored by NavAir. TransWave Photonics, or TWP, is a small business located in Austin, Texas, that specializes in mid-wave infrared photonic systems for the defense and commercial market. Since 2016, we've worked at the forefront of photonics research, executing multiple SBIR and STTR contracts to generate non-dilutive funding for our work, which has led to protected intellectual property for laser and LED technologies we've developed. Some of the key resources that TWP brings to bear on complex photonics challenges are the amazing technical team that we employ, all with strong backgrounds in photonic research. Through our partnership with the University of Texas at Austin Microelectronics Research Center, we have access to over 12,000 square feet of equipment, clean rooms, and manufacturing technology that no other small business can match. Because of these resources, we are already operating as a mid-infrared LED array supplier for commercial infrared scene projector manufacturers. If you have a photonics need and want a reliable supply chain provider, look no further than TWP. When we talk about infrared, we're talking about a spectrum of light that can't be seen by the naked eye. Several weapon systems use various infrared, or IR, wavelengths to help guide the weapon to its intended target. The current state-of-the-art when testing these systems is to use an IR projector to simulate a target or laser designator, and then see if the weapon system reacts to the projection as it would in real life. In 2021, the Navy came to us with a particular photonics challenge. The current projectors are limited in their brightness, frame rates, and size. They also use a lot of power, requiring special outlets to use, and are highly inefficient, generating a lot of wasted heat. Could we help the Navy by making a high-fidelity, efficient IR LED that shines brightly in a specific mid-wave wavelength? From the start of the SBIR project, our goal was clear. How could we improve on the conventional mid-wave IR LED? With the same power input, we wanted to improve efficiency tenfold, generate an infrared scene 3 times brighter or hotter than existing LEDs, all while operating at room temperature. Our team of experts decided to use resonance to solve this challenge. You've experienced resonance yourself in many different ways. For example, when music vibrations match the natural frequency of your body cavity, you can physically feel the rumble of the bass as your body matches that frequency. When this happens in optics, we call it the Purcell effect. By implementing a resonant cavity in our LEDs, we can significantly enhance the yield without having to increase power input, leading to a brighter output compared to conventional LEDs. By proving that we could use resonance for power enhancement, our sponsors at NavAir chose TWP as the sole Phase 2 contractor to develop a new prototype mid-wave IR LED array. After 2 years of research, we've constructed our first LED demonstration array and plan on having a large array for demonstration by the first quarter of fiscal year 26. Our goal for this project is to have a finished LED array ready for integration in 2026. After that, a completed projector prototype will depend on the sponsor's feedback, as well as our projection manufacturing partnership. There are some risks still left in development, which we are addressing now. For example, a high-yield Purcell LED may not be cost-effective. Therefore, we have prepared a less stringent manufacturing process that significantly reduces cost, without sacrificing the necessary yield and performance needed by the Navy. Also, there are concerns about hybridizing or integrating our LED array with a read-in integrated circuit, which controls operating conditions like current and voltage. Our LED array and the integrated circuit need to work together to control a projection image that maintains a high degree of brightness and uniformity. We're solving this issue by manufacturing 2 arrays with different hybridization methods to ensure that we deliver an operable LED that meets required performance. Our goal, by the end of our Phase 2 option period in 2026, will be to have a large array with a high density of mid-wave IR pixels that can demonstrate our stated goals, a tenfold improvement in efficiency compared to existing LED arrays. Our LEDs are superior to traditional mid-wave IR LEDs in all the ways that matter to the Navy. Compared to the current state-of-the-art, we're projecting a 10-fold increase in power efficiency while operating at room temperature, without the need for additional cooling. This gives our LEDs distinct advantages, particularly with size, weight, power, and cost, otherwise known as SWaP-C. Higher efficiency LEDs mean that even with brighter LEDs, there is less heat generated, and therefore less cooling required. Less cooling means we can design a lighter projector, enhancing SWaP-C. The benefits to our customer, including the U.S. Navy, are that they receive LED arrays with high fidelity, improved reliability, and enhanced operability. As a quality vendor, TransWave Photonics prides itself on staying on schedule with our R&D projects, while obtaining the performance required to satisfy the high bar for Navy technical leads as we continue improving on our mid-wave IR LED designs through continued testing, demonstration, and evaluations in increasingly relevant environments. As we progress into our SBIR Phase 2 option period of funding, we're actively looking to find and engage with transition advocates, technology champions, and relevant stakeholders, such as those individuals working with the Navy, Air Force, and Army on testing advanced tactical aircraft protection systems that include infrared sensors, or other hardware-in-the-loop test scenarios that need improved infrared projectors. Funding is key. TWP is confident that with our experience, we can continue to optimize our existing prototype for the needs of our customers while improving TRL to acceptable levels for acquisition. In addition to the defense need, TWP also understands that improved mid-wave IR LEDs can in turn be used in commercial applications, making sensors more efficient, with higher fidelity and more reliability at higher temperatures. The infrared LED market is forecast to be a sizable $1.8 billion by 2032, with a compound annual growth rate of over 15%, making infrared LED technology a good investment. We are also confident that our timeline for marketing single-emitter LEDs is within reach, with an estimate of full-scale manufacture by 2027. This short timeline, accompanied by the market forecast, means that TWP has high revenue growth potential within just a few years. Because we are intent on getting our LEDs to market, we've focused our initial market to our known customer, the program offices involved in hardware-in-the-loop testing. For this, we need to continue outreach and collaboration with our sponsor, stakeholders, and technology champions. While the Navy is our first target customer, the Air Force and Army are also important customer targets for early adoption. Secondary customers include addressing the mid-wave infrared research and development needs for federal laboratories, including the Navy and Air Force. We also would like to engage with companies working with the Army to develop next-generation imaging solutions for soldiers, since our projectors will be the next generation in necessary testing technology. As we continue to partner with both government and industry, TransWave Photonics will continue ensuring the superiority of our mid-wave IR LEDs, both in higher efficiency and the potential for room temperature operation with improved performance over current LED options. Finally, there are many interesting commercial applications that we'd like to contribute to, either from distribution of our LEDs to original equipment manufacturers developing low-cost and low-power sensors and diagnostic technologies, or through additional custom development of our LEDs for clients. Taking advantage of the mid-wave infrared wavelengths means that advanced low-power, low-cost sensors can better monitor gases like carbon dioxide, volatile organic compounds, and methane. Monitoring these gas levels can help with the construction of smart, energy-efficient buildings, physiologic monitoring for warfighters, aviators, and medical patients, oil and gas production, and hazard monitoring for various chemical and biological hazards. Do you have LED photonics needs? If so, we're excited to speak with you as well as sharing in our progress and new discoveries. Please don't hesitate to reach out to Sean Jung, our CEO, through one of the following methods, or visit our facilities in Austin, Texas. We look forward to hearing from you soon.